Welcome back. Today we're be starting Unit 3 in this honors geometry course, which will cover congruent figures. If you haven't watched my previous lesson, 2.8, I recommend you do so, but let's get right into it. So, congruent figures, right? How can you tell if two figures are congruent? Well, if you think about it, two geometric figures, they're technically considered congruent if one of them could be placed on top of the other, right? Because if that were the case, then that would mean every single point would fit on top of each other, right? Every single side, every single angle would fit on top of each other, right? So therefore, like if you see this visual here, right? If you took figure A, right, and you place it on top of figure B, well, you would find out that they're actually going to be congruent figures because they match exactly, right? I mean, if anything, in this specific diagram, B just looks like it's a bit rotated, but um, if you can place every point, angle, side, they're congruent, right? So because A can be placed on B perfectly, right, you can say that those two figures are congruent to each other, right? And if you haven't gotten this realization yet, well, congruent figures have the same size and shape, right? Everything about congruent figures are the same, right? Because they're equal. Now, let's focus a bit on congruent triangles, because that's going to be essentially this entire unit, right? If we have two triangles that are congruent to each other, right? So in this case, we have triangle ABC and triangle DEF. Of course, right, you can place it on top of each other. My goal with this diagram is to kind of show you that you can place the top triangle on the bottom one, but what you'll see, an important thing, right, what you'll see about congruent triangles is that all pairs of corresponding sides are congruent, right? What that means is like AB is congruent to DE, right? They're corresponding. They lie in the same like area, right? AC is congruent to DF, right? And likewise, BC is congruent to EF, right? Keep in mind, only corresponding sides are congruent. So, for example, you can't say that BC is congruent to AD, right? They're not corresponding. So, corresponding letters must match, right? When you're stating two congruent figures as well. What that means is, let's say you name this orange triangle as triangle ABC, right? So you start with A, then you go to B, then you go to C. You have to follow that same exact pattern when you're naming the congruent figure. So for the blue one, you would start with D, you'd go to E and then F, right? You have to follow the same path. Okay, more about correspondence. So my goal with this diagram is just to kind of show you how um, corresponding figures, or sorry, congruent figures can overlap with each other, right? Specifically here, you have this, right? Triangle, triangle KIT, right? And it's reflected across this line and it forms this mirror image, right? You might be thinking, well, yeah, of course it's going to be congruent, right? Because like if you reflect an image over a line, right, well, it becomes symmetrical, right? It's just the same exact thing. And yeah, that's right. But specifically for this diagram, I want to just go over what corresponding means, right? So angle I here, right, that corresponds to angle E, right? Because that's the mirror image, right? Angle E is a mirror image of I. Uh, Same thing with like, for example, side KE, right? Side KE and KI, they're also congruent, right? They correspond with each other. Likewise, TI and TE are also corresponding, so therefore they're also congruent. So yeah, just make sure you're naming that the corresponding parts are congruent to each other, right? That's the key thing. And actually, if you notice, well, what about this side of the triangle, right? Of both of these. Well, you could actually say that KT is congruent to KT, which may seem obvious. Well, yeah, of course it's going to be equal to each other, but you'll realize that's actually a really important step to take when you're trying to prove two things congruent. So once again, there's actually a property for that. Um, right? KT reflects onto itself. It's a side shared by the two triangles, right? And therefore, like I said, you can say KT is congruent to KT. The reason is this very important property, the reflexive property, which states that any segment or angle is congruent to itself, right? So of course, KT is congruent to itself. Again, that might seem really obvious, but as we do more proofs, it will make much more sense why we need that property. Okay, so now my goal is to go over some example questions that kind of review what we have learned so far in units 2. I think maybe some things in 1, but first I want to let you guys try these problems before, of course, I approach them. So this is the first one. Assuming you have given a try, right? Here we have triangles PQR and SQT are congruent to each other, right? So once again, we have PQR and SQT, they're congruent to each other, right? What's the reflexive element? What that's asking us is what element between these two triangles is reflexive in nature? What is shared between both, right? Well, if you look at these two figures, right, think about this. So you have PQR and you have SQT. You'll notice that both of them share the same angle here, right? Usually, when two triangles, or just two figures in general, if they share the same component, that's the reflexive component. So in this case, this is a reflexive component here, right? Angle TQR, right? So once again, that's going to be angle TQR, right? Because that's shared between both of the congruent figures. Okay, this is a larger problem, but once again, I'd like to give you guys an attempt. Okay, assuming you're given a try. Here, I've labeled everything we know, right? Of course, we know M and N are midpoints, so I've labeled, um, well, I haven't labeled that, but just keep that in mind. DC is congruent to AB, uh, right? I've labeled that in red, and of course, the other congruencies. So let's look at our first conclusion we're trying to make. We're trying to conclude that angle ADC is congruent to angle ABC. So that is referring to this angle and this angle, trying to prove that they're congruent to each other. What property can we use to prove that? Well, here we have these angles, right? The purple and orange angles, they're congruent to each other, right? Or at least like the purple angles are congruent, right? And the orange angles are congruent. Well, if you're trying to prove that this entire angle is congruent, well, you could just add those two, right? So this will be a classic example of the addition property, right? Because you're adding congruent angles to give you congruent sums, right? Let's look at B. CM is congruent to AN. So CM is congruent to AN. How do you prove that? Well, think about this, right? We know that this entire segment here, DC, right, the red ones are congruent to each other. So DC is congruent to AB. And I told you earlier to keep in your head that M and N are midpoints, right? Remember, whenever we have midpoints, right, in a problem, and we're trying to prove that something smaller is congruent, right? Given that something bigger we know already is congruent. So in this case, we know that the red segments are congruent. And because we know that M and N are midpoints, it was a very, very strong cue that we have to use the division property, right? Because if two segments are congruent to each other, right, then their like divisions are congruent. In this case, those two are congruent. Those are the divisions. Okay, BD is congruent to DB, so we're saying segment BD is congruent to DB, well, you'll realize this is the same segment, right? It's the same exact segment, so it's actually what we just learned, reflexive. The reflexive property. And finally, let's look at part D. You have DC, right, is congruent to DB, right? That might not seem obvious as to how to prove in the problem, but let's look at what we're given, right? We're given that DC is congruent to AB, and we're given that AB is congruent to DB. What you'll realize is there's actually an overlap, right? Watch, look at this, right? Both of them are congruent to AB. I'd said many times in a specific lesson that anytime we have an overlapping part, it's a good sign that you have to use the transitive property. So in this case, you can say this is the transitive property, right? The reason is, well, if we have two segments, right, that are congruent to the same segment, they're going to be congruent to each other, right? So DC will be congruent to DB because both of them are congruent to AB. So that's that question. Let's move on from there, right? Similar thing. I'd like you guys to do the same thing for this problem. All right. Once again, assuming you're giving it a try, let's look at this. So of course, I have marked everything in the negative diagram, right? Let's look at our first conclusion. QFG is congruent to RGF. So QFG, right, which is this angle, is congruent to RGF, which is this angle. How do you prove that? Well, in the problem, right, we're given that there's two angle bisectors, and we know that angle 5 is congruent to angle 7, right? Those green angles are congruent, and you know that these are angle bisectors. Because we're trying to prove that this entire angle is congruent to this entire angle, well, think about this, right? We have angle bisectors in the problem, and we have a smaller pair of angles that are congruent to each other, right? So that's a good sign that we have to use either the multiplication or division property. In this case, we have to use multiplication because we're trying to prove that something bigger is congruent, right? So this will be the multiplication property, right? Let's look at the next one. QP is congruent to PR. So that's referring to, let's see, QP is congruent to PR. So QP here, right, is congruent to PR. How do you prove that? Well, we know that the purple segments are congruent to each other, right? Because again, that they give us in the problem. And we know that these orange segments are also congruent to each other, right? FP is congruent to PG, right? So how do you prove that these are congruent? Well, look at this. You have this entire segment here, and if you subtract this part, you get that, right? Similar logic. You have this entire segment here. If you subtract this part, you get this, right? So this is a classic example of the subtraction property. So this is subtraction, right? Next up, we're trying to prove that angle 7 is an acute angle. Well, here, right, of course, it might look like angle 7 is acute, but again, don't make that assumption. What do we know? We know angle 5 is acute, right? And we know that angle 5 is equal to angle 7. Well, to me, that screams one specific property, right? If you know that angle 5 is an acute angle, and we also know that angle 5 is equal to angle 7, well, you can say that angle 7 is also an acute angle because of the substitution property, right? You can substitute that acute property of angle 5 into angle 7, right? So this is going to be substitution. Once again, that doesn't make sense. You are taking the fact that angle 5 is an acute angle and you're substituting that into angle 7 because you know that angle 5 and 7 are equal to each other. Lastly, let's try to prove that angle FER is congruent to GEQ. So FER, which is this, right? FER is, is congruent to GEQ. Well, you'll realize that they're the same angle, right? They're just named differently, but of course, right, an angle can have many different names, but it's just referring to this angle, right? Of course, this is again a classic example of the reflexive property, right? Because you're saying that one in the FER, right, an angle is congruent to itself, right? So once again, that's a reflexive property. Okay, I'd like you guys to try these problems too before I dive into it. All right, so let's look at this one. Here we have triangle ERC, right? And ERC here. We're trying to prove it's congruent to another triangle. Which one would it be? This is where the corresponding things come in. Corresponding concept comes into play, right? If you're starting at E, go to R, and then you go to C, right? Well, let's follow that same logic, but with the other triangle in this problem. So now you know E is a right angle, so you know you have to start at a right angle. You have to go up to angle R, or like you have to go towards angle R. So in this case, we have to go towards angle C, and you're going away from angle R. So now you're going away from angle C, right? Follow that pattern, right? So here we have angle triangle ERC is congruent to triangle TCR, right? Lastly, why is RC congruent to RC? Well, yeah, this is reflexive property, right? It's congruent to itself. Okay, same thing with this, right? We have triangle BOW, right, which is here, BOW, right? We're trying to prove that's congruent to what other triangle? Same thing, right? We're starting with B here, we go towards O, and then back down to W, follow that same pattern. You're starting at Y here, you're going towards T, and you're going back down to W. So it's congruent to Y, T, W, right? You can also just think of this correspondence as a mirror image, right? That's why I showed you that kite earlier, or like remember this specific example, right? If you think of this as a mirror image of this, it becomes much easier to decide the corresponding parts, right? Because they're reflected across this kind of imaginary line that you can think of. Lastly, why is angle 1 congruent to angle 2? Well, here, right, you'll actually realize it. And this might actually not be that easy to kind of follow, but you know that this angle and this angle are equal. You know that this angle, right, and this angle are equal, right? I'm going to clear some of the marks I made, right? But anyways, right, we know this angle is equal to this angle, and that this angle is equal to this angle, right? So let's just give numbers, right? Let's say that those blue angles, right, were like 50 degrees. Those purple angles were like 40, or actually, let's say they're 70, right? So what can you conclude about angle 1 and 2? Well, remember that all angles in a triangle add up to 180, right? So if you do 50 plus 70, that gives you 120. So this has to be 60, and this also has to be 60, right? Because again, 50 plus 70, that's 120, and you do 180 minus 120 to get 60, right? So the reason those two angles are congruent to each other is because, well, two reasons, right? First of all, these two triangles are congruent to each other, right? Because these two triangles are congruent to each other, every single angle, all right, every single side, every single vertex that they share, they're also going to be congruent to each other. And I'm going to dive more into that in a later lesson, but that's one of the big reasons why, right? Also, if you just calculate this mathematically, well, you'll realize they both have the same measure, right? So that's another way you can prove this. So hopefully this example, or all these examples here, made sense. If you have any questions, please leave it down in the comments. But I'll see you next time.